So last topic in the module 2 is a subspaces and null spaces. Most important is subspaces because null spaces depends on linear transformation, but linear transformation is not in the first in our module, second module. That's why I skipped the null space. But anyhow, I explain what is a null space. First of all, you learn about subspace, and based on the subspace, we do the sum problem. So what is a subspace? First of all, you take one vector space, usually vector space named as V. So every vector space depends on some field. Let V be a vector space over the field. Now this time you take some subset of V, W, say. So W is a subset of V. This W is said to be a vector space, vector subspace because it is a subset of V. Already one vector space is there. This is a subset of previous vector space. Now this W is also a vector space over the same field, then it is called a vector subspace of the given vector space V because it is already vector space condition satisfies, as well as it is a subset of another vector space, so it is a subspace. So this is the definition. Actually, this is the theorem. Vector space means with respect to addition, abelian group, scalar multiplication, and other four properties. This is the theorem. You just remember the statement of the theorem only. No need to learn the proof. Anyhow, I provide the proof also. Most of the problem are proved by using this theorem statement only. A non-empty subset W of V is a subspace of V, a vector space V. A non-empty subset W of V, W of V means W is a subset or equal to V. V is a subspace, W of V is a subspace of V, vector space V, if and only if each pair of vectors alpha comma beta in W and each scalar C in field, the vector alpha C alpha plus beta is again in W. You take two vectors alpha comma beta in W and take any scalar. Here also any vectors alpha comma beta or any two vectors in W. You take two vectors in W and scalar C in F, then the linear combination C into one vector, anyone, either alpha or beta, plus another vector is again in W. Then it is a vector space. This is the theorem statement. So now here I provide the proof. So if you have any interest, you can read it. Now next, I am going to directly going to problem. So we prove the problems using the above definition. So first problem. V is any vector space, then show that V is a subspace and show that the subset consists of the zero vector is also a vector space. Okay, every vector space has at least two vector subspaces. So one of them is itself, another one is zero vector space. A zero vector space is called trivial vector space. Answer. So in place of W, we know that as per set theory, we know that every set is a subset of itself. Every set is a subset of itself. Therefore, V is subset or equal to V. First part over. Now you take two vectors in V, in this V, alpha, beta. So alpha comma beta. If you have any doubt, give the name W equal to V, which is subset equal to V in W, which is nothing but V, arbitrary vectors. And take a scalar C in field. Now, these are in subset in W, alpha, beta in W. These two, what about previous theorem says that if W is a subspace, if and only if alpha C into alpha plus beta is in also W. Now we want to show that C into alpha plus, what about C into alpha? C alpha. Alpha in V. W means W nothing but V. So V already vector space. Therefore, vector space satisfies the scalar multiplication. It is in W. Since C in F alpha in W, which is nothing but V. So C V is a vector space. C alpha is in V because vector space. V is a vector space. Now C alpha belongs to W, which is nothing but V, and beta belongs to W, which is nothing but V. It means C alpha in vector space V, beta in vector space V. Therefore, as per vector space condition, C alpha plus beta in V. V nothing but W. Since a closure property of abelian group, because V is a vector space, so it is a abelian group with respect to addition. Closure property means sum of two vector is also in the same vector space. Since V is a vector space. Here also, because C is vector space by closure property, here scalar multiplication property, here closure property of addition. Okay, so therefore, we start from C alpha comma beta in W. Finally, we show that C alpha plus beta in W. W nothing but V. As per definition, hence V is a vector subspace of V. That means every vector space is a subspace of itself. Next part, zero vector. Other part. This is part 1. Here we need to show that two parts. Next, to show that 0 is a vector space. Additive identity. We know that 0 be the 0 be the additive identity in a vector space V over F, as your wish. You can write on over F, otherwise leave it, no problem. That is 0 belongs to vector space. Now consider, otherwise it is better to write on. So take 0 vector, that implies 0 taken in a set form. It becomes subset or equal to V. In place of W, we have a V. W equal to singleton set 0. Now you observe that take alpha comma beta from W. How many elements are there in W? Only one element. It means alpha is 0, beta is 0. We are not, I am not said, I am not all, here my intention is alpha comma beta are in W. These two may be equal or unequal, secondary. If these two are distant, I will inform to you before alpha comma beta are two distant elements. If you distant elements, that time we write down as mathematically alpha comma beta not equal to 0, which belongs to W. Likewise, alpha comma beta belongs to W means they may equal, may not equal. All possibilities, two possibilities are there. Okay, you understand that? It means alpha equal to 0, beta equal to 0, because alpha is an element of W. In the W belongs to W means it is any one of the element, but we have only one element, beta equal to W. Now, C belongs to F. Take. Therefore, C alpha equal to C into 0, which is equal to 0, which is in W, which is in W. Okay. One more thing, beta is also equal to 0. Find value of C alpha plus beta. We want to show that C alpha plus beta in W. It means this value equal to 0. C alpha is 0. This value is 0 by the above. Plus beta value is 0. 0 plus 0 equal to 0, which belongs to W. W nothing but singleton set 0. So, as per previous theorem, C alpha plus beta in W, therefore W is a subspace of W equal to singleton set 0 is a subspace of vector space V. That's all. Every vector space has two subspaces, right? Itself and zero space. This is the first problem. Now we are going to second problem. Fn. Here I provide the two problems in the same question. Already we know that n-dimensional space is a vector space. For understanding purpose, I am telling you Fn means set of n tuples x1, x2, and so on xn. Each xi belongs to F, field F. In place of V, this set is there. We know that already we proved in the first topic, vector spaces topic, Vf, which is nothing but F power n over F. Same F power n over F is a vector space. Vector space. Here x1, x2, x3, xn are any values in field F. Values means scalar. We usually called scalars because elements of field are called scalars. Elements of vectors are V are called vectors. So first question. Now take a subset. Answer for A. Take W. Here W value is this thing. Set of all n tuples from Fn. Set of all n tuples from this set such that whose first component is 0. Xn. Such that x1 equal to 0. This is belongs to previous set V. You understand means this is belongs to this Fn or V such that x1 equal to 0. It means clearly it is a subset of Fn because you take all the elements of Fn such that whose first component is equal to 0. So non-zero first component vectors also belongs to Fn. Zeros, non-zeros all are belongs to. But we collect only first component 0 vectors from Fn. We want to show that W is a vector space. First question. As usual, routine procedure, take two vectors alpha comma beta from W. So as per hypothesis, alpha equal to, it is a n tuple x1, x2, xn. This is belongs to Fn such that 0 means you keep 0. It is better, easily understand. X1 value should be 0. Here replace 0. X1 value is 0. And beta equal to 0, y2, y3, and so on, yn. These are belongs to Fn. Obviously, it belongs to Fn. If you have any confusion, leave it Fn also. Or you understand? Now, our question, our goal is C alpha plus beta. Now take C from field. What is the C alpha plus beta value? C alpha plus beta value. Evaluate this. C times of alpha value 0, x2, and so on, x3, and so on, xn, plus beta value 0, y2, y3, and so on, yn. Send the scalar inside. C into 0, 0. C into x2, cx2, C into x3, cx3. Component wise multiplication. 0, y2, y3, and so on, yn. Now, sum of two vectors is a vector adding component wise. 0 plus 0, c x2 plus y2, and so on, c xn plus yn, which is equal to 0, c x2 plus y2, and so on, c xn plus yn. x1, x2 are elements of F. Therefore, C is also element of F. This is an element of F. This is element of F. All are element of F. This is also element of additive identity. F into F into F, F power n. This is an element of F power n. in which first component is 0. Therefore, it belongs to W. You understand? So, Fn this is a element of V. So, C alpha plus beta belongs to W. As per definition, we say that W is a vector subspace of V. Second question. Verify this set. Verify means may or may not. Verify this set, which is a vector space or not, part B. But they provide the relation. Two parts. First part for A, answer for A, answer for B. Not part B. For answer for B. Here W equal to n tuples vector x2, x3, and so on xn, which is belongs to given set Fn, such that the first two components have this relation. First component equal to 1 plus second component value. This is the given hypothesis. Whatever the vectors in Fn satisfies this condition, taken into one set, the name as W. As usual, routine procedure. Take two vectors and one scalar. So, alpha beta in W, the vectors in W is in the form x1, x2. So, x1 value is depends on x2. So, if alpha depends on alpha is in the form x2 plus 1, x2, because x1 value is 1 plus times of, if you have doubt, write down first x1, then x2, comma x2, then x3, and so on xn. Similarly, beta equal to 1 plus y2, give some variation, y3, name variation, because these two may or may not equal, or in W, is in the form. Because every vector in W is in the form. First component equal to 1 plus second component. Now, estimate the C alpha plus beta, routine procedure. Now, what about C alpha plus beta value? C times of 1 plus x2, x2, x3, and so on xn, plus 1 plus y2, y2, and so on yn. Simplify this expression. C times of C times C plus Cx2, Cx2, Cx3, and so on Cxn, 1 plus x, y2, y2, and so on yn. Now observe that this is nothing but sum of two vectors. As you know, component wise addition here. Y3 plus and so on Cxn plus yn. Now observe that what is the first and second relation, whether it is a 1 plus second component or not. Now here first component C plus Cx2 plus 1 plus y2. This is the first component. Second component value is 1 plus, add 1 to the second component. These two are equal or not? These two are not equal, because if these two are equal, it means second component. Suppose say Z2, this is Z1. Here, this vector belongs to W, then Z1 equal to 1 plus Z2. Test whether Z1 equal to 1 plus Z2 or not. Here we have 4 terms. In the Z1 we have 4 terms. Z2 we have 3 terms. 1, 1 matching. y2 y2 matching, cx2 cx2, but here c is there additionally. C is a scalar, it may be 0 or non-zero, which is not equal to 0. Test z1 equal to, here I write down neatly, but you can understand. Test whether z1 equal to 1 plus z2 or not. It is clearly not equal. y2. That implies C alpha plus beta does not belongs to W. Therefore, it is not a vector space. Therefore, W is not a subspace of B. That's all. So next problem, I can prove only one problem. Later remaining problems, try to yourself. Show that the space of polynomial functions over the, already in the first part I proved the set of all functions form a vector space. Now here I am taking polynomial functions. Polynomial nothing but a function. So function need not be a polynomial. Sin x is a function. Cos x is a function. E power x is a function. X plus e power x is a function. They are functions, not a polynomials. So now here third question. Consider W equal to set of polynomial. Polynomial is in the form a naught a1x plus an x power n, where f of x form a is belongs to field, okay, where n is a positive integer, when is a natural number or non-negative integer. Usually 0 degree is also available. That means n union 0. Clearly, V is a subset or equal to V, because V is a function, polynomial also a function. So V contains all functions, but W contains only polynomial functions. So V contains all function means polynomials also there in V. So W means only polynomial functions. So take two functions. Let f of x, usually functions names name as f of g of x. F of x has some degree, second degree or third degree. For example, I am considering nth degree. And g of x has also have some degree. I am considering here nth degree, mth degree, not nth degree. First one m. These m equal to n or m not equal to n. Both are possibilities. Now take and alpha c belongs to field f. C alpha c f of x plus beta. Test this. Beta means g of x. Here, if you have confusion, this is alpha, this is beta. G of x, f of x. C alpha plus beta equal to C into f of x. Now, substitute the values. M may be less than n, case 1. Let these two are integers, m and n. They are equal, are equal. Let m less than n. C times of, here we get am x power m, am plus 1, x power m plus 1 plus and so on, an x power n plus other part as usual. Now adding up to, here we have m terms, here we have m terms. These are the additional terms more than m terms, remaining part. Adding these vector directly. You know the polynomial addition, scalar, first term, x coefficient, adding x coefficient, likewise, mth coefficient. Okay, that's clearly you understand that it is a, you observe that it is a polynomial of degree, nth degree, all coefficients belongs to field. So, which belongs to W, because it is also a nth degree polynomial. Therefore, W is a subspace of V. That's all. Null space, I leave the concept, but I explain what is a null space. Before going to null space, range space, null space is there. Range space, null space, and a linear transformation. A linear transformation, nothing but a function from one vector space to another vector space. For example, vector space V. This is another vector space W over the same field. It is a function. This function satisfies T of, suppose here you take two vectors x, y. Here addition is possible, x plus y. X plus y is also a member in the same vector. This is mapping to T of x image value. This is T of y. This image value is T of x plus y. This have some relation. If this function satisfies this condition, satisfies means the image values have the relation. In addition that c into x in v, cx is also a v. This image is T of cx. This is same as c times of T of x. If these two conditions are satisfied the given function from V to W, then this function is called LT, linear transformation. Linear transformation. Null space means the set of vectors mapping to 0. Null space of LT. Let T be a vector space from V to W. Then null space N of T. Null space of T nothing but set of all vectors x belongs to domain set such that their images are equal to 0, because additive identity in W also 0. Here 0 is there because it is a vector space. T. Right side also 0 is there. Here also 0 is there. Here also 0. The 0 is mapping to 0 as per hypothesis. These two conditions, if the function satisfies these two conditions, it's called a linear transformation. First of all, it is a LT. It is a LT. T is a LT. LT is T. So substituting in LT, you observe that 0 is mapping to 0. Put x equal to 0. X equal to 0. 0 plus 0 in the left hand side in the first property. T of 0 plus 0 means T of 0. 0 plus 0 equal T of 0 equal to T of 0 plus T of 0. In the right hand side, you have 2 times of T of 0. In the one left hand side, 1 time of T of 0. Simplifying it, we get T of 0 equal to 0. That means 0 is mapping to 0. So it is a non-empty set, first of all. N of T is a clearly 0 belongs to N of T. That implies N of T is a non-empty set. And it is a vector space, vector subspace. N of T is a vector subspace of domain space V. This space is called null space. Null space. So, and this is the theorem, but in our syllabus, they mention only null space. It is difficult to cover null space without covering linear transformation, range space. So I leave this part only. You just remember the null space definition. If T is a vector space, T T is a linear transformation from vector space to another vector space over the same field. Collect a set of vectors from the domain set such that their images equal to 0. This set form a vector space. This space is called a null space. Vector subspace. This subspace is called a null space of the transformation, null space of the given transformation. That's all. This is the last topic of this unit. Remaining problem, try to yourself. I provide all the problems, many problems. Okay, here I am stopping. If you have any doubt,